All right, welcome back, everyone. I hope you had a chance to visit the expo and enjoy the amazing sponsor booths and showcase there. We'd love to see your highlights on social media, so please keep sharing them using the hashtag YouthSTEM MastersConf and tagging YouthSTEM2030 either on Twitter or Instagram. Now, though, we're on to our final talk of the day, so I'd like to welcome Professor Michael Saliba, a solar cell researcher at the University of Stuttgart. Michael is a professor and director of the Institute of Photovoltaics at Stuttgart University, with a dual appointment at the Research Center, Jülich, Germany. His research focuses on a deeper understanding of novel semiconductor materials such as perovskites, again, apologies if I mispronounce anything, for a sustainable energy future. Here with his talk, Novel Materials for Solar Cells. Over to you, Michael.
So I'll jump right into it. Thanks a lot for the kind invitation to Mari and to Lewis as well. It's been amazing. I've seen some of the talks and I really want to congratulate you on this great initiative. So let me jump right into it. I think I'm honored to be a guest here and to sort of say a few words on sustainability. And I'm so enthused, and it's such a pleasure to see that at such a young academic age, you're already starting working on this topic as well. So I want to sort of change gears a little bit towards novel materials for solar cells, and solar cells maybe in general, and how this can contribute to the SDGs as well, for instance. So first of all, let's get on with it here. This is Stuttgart in the southwest of Germany, kind of here, and that's also where the Institute for Photovoltaics is located, which is indicated by the solar cells on the rooftop, actually. So this is how you can find us. And if you ever want to come by, please do so. Just drop me an email. Anyone is welcome. Solar cell research is for everybody, so please feel free to join. Then here, in terms of the SDGs, if you look at them, I mean, we are kind of firmly placed here in affordable and clean energy. The other activities, of course, are important as well, but that's sort of where we see ourselves in terms of creating affordable and clean energy. And why is that? So this is an interesting figure. You can see here how, let's take the right-hand side first, how there's a lot of energy in sort of fossil fuels, coal, uranium, oil, and natural gas. The problem is, however, firstly, it's limited, but then secondly, it also creates a lot of CO2, as you all know, and that's sort of what creates so much trouble for us at the moment. And if you look at what we need in terms of electricity, it's about 16 terawatts per year. You see that here. It's a relatively small amount of what can be produced, for instance, by wind, biomass, hydro, and so on. So here on the left-hand side, you see all the renewable energy, which replenishes itself each year. And the real elephant in the room is this yellow disk, and that's the sun. Okay, the sun is producing plenty, 23,000 terawatts each year. To give you another figure to think about, 1 hour of sunlight that is received on Earth is enough to provide electricity for the entire planet for a year. So 1 hour is enough for a year. So, you know, and that's kind of what gets people very excited about this topic. And that's sort of where we can make a contribution and an impact for a sustainable energy future. And this is by far not our own idea. Many people had it here, the ancient Egyptians, you can see it on the murals already. They already wanted to harvest the energy of sunlight. They even wanted to store it. So there's here even a relationship to battery research as well. And there's another very nice figure here, which was created quite some time ago. But the important thing is it's very full with stuff. But here we have the Sahara Desert, and an area of this size here, for instance, would be enough to power the entire planet. If these were solar cells, it'd be enough to power the entire planet with electricity. Of course, it's difficult, you know, to move the energy around. There's the US, there's Asia, and so on. But still, you know, just to give you an idea, this would be enough. A smaller area, more modest, would be sufficient to power the European Union, or the Middle East and North Africa would be a smaller area still, and so on. So you see, there is, in principle, there is space, and there are also ideas towards it. It's also, let's say, the willingness to move into this area in order to go more sustainable, which is a little lacking sometimes as well. Because if you had to guess how much electricity is actually worldwide produced by solar, although it can sort of sustain us indefinitely almost, you can see that here. This is the total energy provided in 2019. You can see almost all of it is from fossil fuels, and then hydro, that's quite some proportion, dams and so on. But then here, this small green portion here in this pie chart, that's less than 2%, and that's renewable energy, and within that you have photovoltaics, solar cells as well. So it's less than 1%. So there's still some space to go up here. So we can do better, and we should do better. Maybe within this decade, the next decade, we can make this grow more and more, such that it becomes so abundant that the others become even expensive compared to it, especially the fossil fuels. And we're working very hard towards it. This is sort of how much solar cells are installed each year. And this is a projection to 2024. And you can see how worldwide this has been a huge effort. In Asia, the US or the Americas, let's say, India, Japan, Germany has installed quite a few. The European Union is very aware of this topic as well. In Southeast Asia too. So this is really taking off. But the question is, what can we do? What can we do, for example, here at the Institute for Photovoltaics, but also what can you do in order to accelerate this development? Because although this looks very impressive, it's not quick enough. We need to be faster still in order to prevent going up more than 1.5 degrees in the next decades, because that'd be detrimental for all of us. And maybe an analogy I'd like to make here is, it can be seen here, we need a technological disruptive situation. And here, this is in 1900, somewhere in New York, one of the streets. And you can see here, all of them rode horses. They had horse carriages. And there was this, let's say, pioneer with a car, a horseless carriage. So the kind of technology freak, so to speak. And then within a decade, however, the situation is completely reversed. You see that here. It's only one person with a horse carriage, only 13 years later. And then technology has taken over because it's cheaper in maintenance to have cars and so on. And the question is, so we are now in this situation here, and how can we manage within 10 years or 11 years to get to a situation like this one, where we have solar panels everywhere, where a lot of our electricity is catered for by solar cells exclusively. And for this, we need nothing short of a miracle. And this miracle can come here. That's the research in the form of a mineral in so-called perovskites. Perovskites are these minerals here. You see it here. They adhere to the crystal structure of calcium titanate. It's a rock that you can find here in Europe, for example, but in many other places as well. There are many rocks. This is one of them, and it has a funny name because it's named after this Russian person here. This is how it used to be. This guy discovered it. He gave the money to the campaign, and so he got to keep the name. So, not so many things have changed in some ways. And now, in terms of chemistry, in terms of research, any material that has this funny-looking structure here is called a perovskite. And one specific material, which works very nicely for solar cells, is something you can see here, where each of these three components that constitute this material is described, the A, the B, and the X component, for example. And when these materials are taken, this was only discovered a few years ago, they can make very nice solar cells. And let me sort of elaborate on those. So first of all, this material is very special because by changing the different components, it can shine light in all kinds of frequencies. So it can cover all the colors of the rainbow, which is visible to our human eye, but it can also go towards the infrared, something that reptiles, snakes, for instance, can see. So we have many different colors, meaning we have many possible different applications from this material group. And this means, similar to the letters in an alphabet, that we can create novel chemistry and novel science from it. And these materials have been shown to be very proficient at constituting LEDs, tunable lasers, batteries. They've been used for computer chips, high power per weight applications here, for example, on a toy plane, and also X-ray detectors for medical diagnostics. And you may say, wow, this is crazy. But of course, this has happened with silicon as well. Your computer chips are also based on silicon. And silicon is also something that is used for the solar cells on your rooftop. So it's not too unusual to have multiple applications from the same material. And that's something that now I'd like to highlight, the silicon solar cell, which is something you see here. It's been developed for almost 40 years, and practically everything which is installed on rooftops or that you see on the side of the road is based on silicon, on this material here. And this new, and now the question is, however, it's reaching its upper limit. There's a theoretical upper limit. You cannot get limitless electricity out of sunlight. And this upper limit, the question is, how can we go beyond it? You know, how can we get to this situation of the disruption? How can we make solar fuel so dirt cheap that it'll outcompete everything? And for that, we need out-of-the-box alternatives. And that's this perovskite material that you see here. Within an extremely short time, it went from 0 to hero. It went from 3.8 to 25.7% nowadays. So it had like a tremendous increase in its efficiency. And mind you, you cannot go beyond this limit here at the top. That's due to the physical limitation. And it's possible to combine the perovskite with the silicon or to have it as a standalone solution. And that's the kind of disruption that we want to work on in this decade and the next decade. And why does it fascinate so many people? You know, the silicon you use in your computer chip is grown in a very complicated way. You wouldn't believe it. Just check it out somewhere online. Growing silicon is very energy consuming, but also like not an easy thing to do. Here, however, this is something we took during my PhD. We use this perovskite ink. We put it on this rotating disc here, and then it turns into this brownish kind of color. And brown or almost black means it absorbs all the sunlight, turning it into electricity. You know, so this is something that is very special. So you use it like an ink that can be printed afterwards. It can be put on substrate that are so light that they can be suspended on a soap bubble, for example. And we can also use with this new material technology which is used in printing, for example. Here, this roll-to-roll processing. You can imagine this is also used for newspapers as well. Or alternatively, these perovskite materials, they can be stacked on top of silicon, which is the established material. And this means the sunlight goes through this perovskite material first, which absorbs mainly the blue parts of the sunlight, which cause you to sunburn. And then the reddish kind of part is more effectively used in the bottom cell, which is the silicon. This kind of architecture, it looks very like sort of complicated and so on, but it's not unknown. It's used for space solar cells. And what we're working on in some ways is to bring space on Earth, you know, to use extremely high technology and to make it so cheap that we can put it on our rooftops, such that it improves the performance of solar cells dramatically. Because already solar cells in some places on Earth are the cheapest source of electricity. You know, in regions which are very sun abundant, there is no reason not to use solar cells. It's so cheap already. But then by putting a second material on top, we can dramatically improve the performance. And that would really sort of give a boost to the entire industry. And maybe even expel the need for fossil fuels in the long run as well. And this, I'll skip through it very quickly. We can stack more and more materials on top under one sun illumination, under concentrators where mirrors are concentrating the sunlight on the solar cell. And with that, we can take the modest silicon solar cell and improve it more and more. And what do we need for that in order to implement it? We need international data sharing in the future in a diverse scientific community. We need to adjust intellectual property rights as well. We need to flip the script as well. So renewable should not just be a nice thing for the planet. Ideally, we make it so profitable that nobody, you know, who wants to make a business could ignore it. So that's one way to incentivize markets and everything as well. And also decentralizing energy supply would be a great side effect as well, because it would change geopolitics, as you can see from the Ukraine crisis at the moment as well. And also we need to rethink new financial models as well. I think you talked about this a lot too, but CO2 needs to be taxed in the future as well. So this would also improve, of course, the price for solar as well, because it's not so CO2 intensive. And then we need to build up the capacity to incentivize collateral industries like electron mobility, batteries, smart grids, the Internet of Things, and so on. And for that, we need a new generation of scientists. This can be any of you. So in your future career, please do consider going into this field and to make a difference and an impact here. So thanks for your attention. Thanks for listening in.
Thank you so much, Michael. That was such an insightful talk, and I think that so many people in the audience will have something that they've taken away from that about how important it really is that we have sustainability in the broadest possible sense in STEM. So everybody, please do join me in thanking Michael in the chat. And it's been such a day of inspiring talks that we have had today, and I think this was a great way to finish our series of talks today. So thank you so much, Michael. And as I said, everybody, please join me in the chat and thanking him for being here today.